Alright, welcome to the next lecture of the week. This one is a completely new topic. It's about the Lambda Calculus and maybe a bit of programming language semantics if we have time. There's only time to do half of these slides because next week I just want to do nothing but review. But I promise you that I will not be testing you on these slides. They are just for fun. They are one last topic, something that I very much enjoy and I would like to pass on to you. It will be useful information though, so I promise there's something in it for you. But let's get started and talk about the Lambda Calculus, okay? I'm here to indoctrinate you. This is the perfect class to do it in. So there are two ways to talk about computation mathematically. There are two main ways to model it. You have your Turing machines, which I think your book has talked about a little bit, and you've probably heard of, invented by Alan Turing. You got like an infinitely sized tape, and you got some boxes that you can fill in on the tape, and you can move the read and write head of the tape. Just old stuff. Sounds like it was invented in the 40s like it was. That's Turing machines. And then if you look at Alonzo Church, who my cat is named after, who was the PhD advisor of Alan Turing, he went and invented the Lambda Calculus, which is an equivalent, okay? Equivalent in power to a Turing machine, first of all. So you lose nothing by talking about Lambda Calculus instead of Turing machines. Equivalent in power to a Turing machine, which is nice. And I and most programming languages researchers are biased in favor of modeling computation using the Lambda Calculus. So I want to teach you about it, okay? Especially because almost every language these days, you got your JavaScript, your Java, your C++, they all have support for these lambdas, right? Which maybe you've already learned a little bit about. So let me teach you some history and where they come from and how to think about them. You can do everything with lambdas, is the idea, okay? So in the Lambda Calculus, this way of modeling computation, every single expression, everything you can write in the Lambda Calculus programming language is a function. You compute using functions. You return functions, you take functions. It's all crazy, but this is how it works. And here's the very simplest function you can write in the Lambda Calculus, and let me teach you how to read it, okay? This is, I guess the parentheses are optional right now, but it's lambda x, then a dot, and then x, okay? So the lambda, which the Lambda Calculus gets its name from, that's just saying, hey, here is a function. I am making a function right now. It introduces a variable, the variable x. That's the parameter of the function. So the lambda introduces, or we also say binds. It takes a variable and gives it meaning. We say binds for that. It binds the variable x. This is the parameter, okay? And so x becomes, this is the name of the parameter. I could have used y, I could have used a, b, c, doesn't matter. This is the parameter of this function that we're making. Of the function. And then the dot is like, all right, I'm done with the parameters. Let me give you the body. So everything after the dot is the body of the function. The body of the function. And this is how you write things in the Lambda Calculus. So this is the function that takes a variable called x, and there's no return statement in the Lambda Calculus. It's just, it gives back x itself. So this is called the identity function, okay? In math, you might write it like this, f of x equals x. In C++, you might write it like this. You'd have to involve some types, though. There are no types in Lambda Calculus, but like, all right, maybe it's the identity on ints. So it returns x. So these are the equivalents in math and C++, for example. But it's a lot simpler to write in the Lambda Calculus. Okay, first of all, no function has a name in the Lambda Calculus. There is no f. Those are things that we have to bring into to use them in math and to use them in C++. But functions in the Lambda Calculus, they're all anonymous. They have no name at all. So this is just the function. The whole thing is a function that takes one parameter and returns the value of that parameter. That is what this identity function in the Lambda Calculus means. And then you might be asking, well, how do you call it if there's no name for it? Like, to call the function, I have to say f of 5, right? Well, No, you don't have to. You can call the function, which is also called applying it. You can apply the function by just putting it next to it. That's how you call the function. You say, all right, here's my function. Here's the lambda calculus, lambda x dot x. And then you can put like a 5 next to it. And this is like, I want to apply 5 to the function. Isn't that nice? And that's how it works. So this is called the identity function, first of all. The function that gives back its value is called the identity function. And so let me show you what happens. You got your lambda x dot x, and you apply it to 5. So this is our initial thing that we give to the lambda calculus running machine. And then it starts executing. So it does a bunch of steps to get this down to a final answer, and those steps are called reductions. So by one step of reduction, we take this 5 and apply it into this function, and just as normal, like when you apply a function, you take the argument and you put it into the body and you replace the parameter with it. So this gets substituted on in here. Subst for substitution. So we substitute the 5 in the body, and this is the notation that we like to use. Like here's the body was called x, and then we would like to substitute 5 everywhere we see x. So 5 for x in the body, and this is our notation. And so that's one step of reduction. If we apply this substitution, so take this x, replace x with 5 everywhere we see it, this ends up giving me back 5, which is what the identity function does, right? It takes what you were given and gives it right back. Very simple. The power of the lambda calculus comes from taking functions and returning functions, okay, which is something we don't really do a whole lot in C++. Maybe I forced you to do it slightly in a previous class if you've taken it with me, but not very much. So let's apply the identity function to itself. We can do that. Lambda x dot x. What do I want to apply this function to? What's the argument? Well, it's lambda x dot x again. This is totally fine. And what we do is we substitute this entire function for x right here. Does that make sense? And give back that answer. So we take this entire thing, put it in as the body, replace x with it. What do you know? We get back the thing we gave. The result is a function, the identity function. It's crazy. Things get a bit weird because there are two x's now. Like there's this bound x, and then there's this whole function that brings in a new x. You have the concept of free versus bound all over again, just like for quantifiers. And so you're allowed to change the name of bound variables as long as you change every occurrence of that bound variable. So for example, lambda x dot x, there's no need to call it lambda x dot x. There's no need to use x. Nobody's forcing you. This is equivalent to lambda y dot y. It's equivalent to lambda z dot z. It's the function that takes its argument and gives it straight back, doing nothing else. Okay? So as long as these agree, it's still the identity function. Okay? I hope that makes sense. So those are bound occurrences. So this binds x. This binds y. It has meaning because it's taking whatever you give when you apply it. But for example, this right here, lambda x dot y, if this is your entire program, the y here is free. It's not bound. Nobody told me what y is. It's just sitting around. Okay? There's a difference there. And it's just like for our quantifier, so that comes back again. All right. You might be wondering if this can model all of computation. I'm going to try and prove to you that it really can. The next thing that you might be wondering about is how do you make a function with more than one parameter, right? We're forced to, like everything in the lambda calculus looks like lambda argument dot body. How do I have a function that takes two things? All you have to do is make a function of the first argument, so have it take the x, and then the body is the function that takes the second argument and does something with it and the first one. Do you see that? That's really cool. So this is like the parenthesization kind of happens implicitly like this. You make a function of the first argument, and then it returns a function waiting for the second argument, and then once it has that, it can do your inner computation. That's beautiful. That's how that works. Okay, so this is called currying, by the way. It's named after another mathematician named Haskell Curry, who also had a programming language named after them. And let me show that to you. So for example, you can make a function that takes two numbers and adds them together, just like a sum function. And you can define it like this: lambda x dot lambda y dot x plus y. That's the body of the inner function. This is the outer one. And you can apply this first to, let's see here, first to 4, and then that'll give back a function waiting for it to be applied to a 2. Isn't that nice? So this is what happens. When you apply this function, how do we step this? How do we reduce this? Well, you do the innermost stuff first, parenthesization, right? So the 4 comes in and it gets substituted in the body of the function. Here's the body of the function, right? It's all this. It gets substituted for x right here. Okay? So we substitute the 4 in for x. And so this becomes, watch what happens with this inner bit. It becomes, well, the body is lambda y dot, then we replace x with its argument. So it's 4 plus y. Isn't that neat? And then that's the whole result here, and we still have the 2 waiting to be applied at the end. Whee! And so I think you can imagine with some more reduction, you end up with 4 plus 2, and then it'll figure out that the answer is 6. Whee! Some dot dot dots. Okay? So that is how you can do computation with arbitrary numbers of parameters. You can make as big of a function as you want. It just needs to take one argument at a time and give back a new function, waiting for the next argument, waiting for the next argument, which is super awesome. So this is called currying, and let me show it to you in Racket, because we can totally do this in Racket. I'll just call everything today scratch.rkt like I like to do. So, I don't know, let's say, let's define the result, or let's just print it. Let's print the result of doing this. Let's take our, I'll do it on a different line so that it's obvious what's happening here. So here's my computation. It's on this line. Lambda, you have to just spell it out in Racket. Lambda x, and then the body is a new function, lambda y, and then the body of that is this x plus y, right? Plus xy in Racket. And so that's the function. And then we want to apply that function first to, what was it, 4? So apply that to 4. Oops, come on now. And then it'll give back another function that we can then apply to 2. And so I'll add another one here, 2. And let's see, is that the proper parenthesization? It's really not happy right now. So that ends there. I think I needed a few more. So that one goes here after 4, and then this one can go here after 2. So that's what that looks like. Okay? Let's see if it's happy with that. And the answer is 6. So it takes the first thing, gives back a function. This whole thing becomes a function, accepting that second argument, waiting for the 2 to add it in. And the answer is 6. So it really works. This is currying. And we can build up all of computer science, all of computation with these ideas. And I think you can tell that I'm very excited about this stuff. It's cool stuff to me. So let's build a programming language. Let me show you how you can do everything that you could ever do in C++ in the Lambda Calculus. Let's build a language. So, okay, let's have Booleans. Let's have true and false. What in the world is true and false in the Lambda Calculus? Because it's just functions all the way down. True, we can define to be this way. True can be the function that takes 2 things and returns the first thing. And then false, I think you can imagine that it's going to be the opposite. So true is a function that takes 2 args and returns the first. So it throws away the second thing. And this one is everything is the same, except it returns the second one. It throws away the first thing. That's what false is. So let's bring that into Racket. Define true to be lambda x, like that, and then lambda y inwards, and then the result is just x. And then false takes everything and returns the second thing. That's true and false. Then, all right, we need to have some way of combining true and false. Like, how do we make and? How do we make or? It all is possible, I promise. So and, for example, can be the function that takes the two things that you want to and, p and q, and it calls them in this very weird way. PQP applies p to q and p as the two arguments. Crazy. So these are the two things you want to and this will work, I promise you. Some very smart people have worked on this stuff, and it's very mind-blowing. These are the two things that you want to and let me show you that it really does give back p and q. Alright? And it uses p and q as functions because they really are defined to be functions. So if we get true as a result, it's going to be this function. If we get false as a result of our and, it's going to be this function. Let me show this to you. So let's and true, not tree, true and false. That's how you apply it. Give it those two things. And let me show you that the answer is going to be false. So this is all equivalent to, well, what's and? It's lambda p, lambda q, pqp, applied to true, which is the function that takes two things, returns the first, and false, which is the function that takes two things and returns the second. With some steps, right? This is going to end up working in this order, right? We're going to do this application first, and this means this will replace the p, because that's the first thing we bring into this function. It's the first thing we call it with, and this is the body in which we replace our p with this value. So that's the first thing we do. So that's going to give us back, all right, lambda q, just the whole body, right, with p replaced with this whole thing. Q dot, well, p is replaced with this, so q dot lambda x, lambda y, x, with another q, and then one more p, so replace it with this again, lambda x, lambda y dot x, and so then we have this whole thing, and we still have this to bring in, okay? Lambda x, lambda y, y. And so this will replace q in its body. Replace q, and here's the body, like here's the function header, and here is the whole body. That's where we're replacing q in, okay? So that's going to be here. We have lambda x, lambda y, x, and then we have q replaced with this whole thing, lambda x, lambda y, y, and then we still have this, lambda x, lambda y, and x. There we go. So that is our intermediate result. Let's bring it in and keep on trucking with it. So we're here. And all right, this needs to keep reducing. We need to bring this in for x and y, right? So essentially what we really have right now, parenthesized, is this. We're ready to make this application. And so this will replace the x in the body here, okay? Replace x. And so then we have, we're getting somewhere, lambda y, but this is the body that replaces x, and x is right here. Oh man, let's replace that with lambda x, lambda y, y, and then we still have all this to apply to right here. We still have this lambda x, lambda y, x to bring in for y, right? Because we're about to make this all happen. But before I get there, let me do some things, because we have a y bound here, and like we're trying to replace y's. It's not the same y, okay? So let me replace these with equivalent things to make this easier to reason about. So let's keep this first y, lambda y, and then instead of x and y here, let's just call them a and b instead, okay? So these are all equivalent though. Lambda a, lambda b, and instead of y, let's use b now. Okay, that'll make it easier to think about. So that's that. And then we want to apply now this original function here, okay? To lambda x, lambda y, x. And now it makes a bit more sense what needs to get replaced, okay? We didn't want to replace y's that were bound, for example. That would have been bad. So this replaces y, that's the parameter in the body here, okay? So this is going to be the body. This is going to replace y. And then, well, is there a y anywhere here? There is not. So it's just the body. There's nothing to replace. It's going to be lambda a, lambda b, b, which is equivalent to, if we bring these back to x's and y's, right? Because we can, doesn't really matter the difference. Lambda x, lambda y, y, which is equivalent to, dun dun dun, false. So this really does do arbitrary computation. It just takes a while. But oh man, that's all you needed? Functions? You could make all of computation? Apparently. Let's do OR a bit faster. OR is this, and we can do it in racket. It's, all right, instead of PQP, take two things, to OR them we do PPQ. Let me show you that this is working. All right. Define OR to be, let's see. I think OR is a, gosh, I'm worried about that because it highlighted it. I'm worried that capital OR is going to be a problem, but we'll try it. We'll just try it. OR can be lambda p, and then it takes the next thing in the inner part, lambda q, and then it applies p first to p, then to q. So p applied to p, and then apply the result to q. That should do it, I think. So that's OR, and now we can OR together stuff. Display OR of true and false. This is, you can't really print a lambda. Well, let's see what it's going to try and do at least. Yay. So that's, okay. First of all, I forgot to apply it properly. I needed to do it this way. There we go. Now it's happening. And it gives me back an answer that is a function, but actually it remembered its name, so thank goodness. So the answer was true. Yay. Isn't that beautiful? Gosh, that's so powerful. All you need are functions. Functions and variable binding. And you can make whatever you want. All right, let's do not. The last piece of the puzzle, then you can have arbitrary circuits being made. If you take in CSCI 45, you know that all you need to make a computer is and, or, and not, right? That's super nice, so let's talk about that. Apparently not is, well, it takes the thing you're trying to not, and then it applies it, because it is a function, to false and true. Are you ready? We don't have to do this in racket, it's going to be fast. So let's try not true. That is equivalent to, well, lambda p dot p. Apply it to false, true. And then, so that's all of not, and then we're applying that to true, which is the function that takes two things and returns the first. And so this, after enough computation, it becomes this, right? We bring in dot, dot, dot. This gets replaced into p. So it's lambda x, lambda y, false, true. Oh, sorry. Lambda x, lambda y, x. That's p itself needs to go there, and then we apply that to false and true. Yay. And if we run this some more, you apply this. Okay, take the x, take the y, and the result is x. Well, x was the first thing, so the answer is false. So it's kind of using the fact that, like, it's eating up one of the inputs to give back true or false. Or false or true based on true or false. So that's how not works. That's pretty neat. Okay, maybe we don't want to make our own circuits. We want to think at a higher level. Let's have an if statement in Lambda Calculus. How do you have that? So here's if then else. So here is your predicate. We call that P. The predicate, your condition. That you want to do your if statement on. So if this is true, do the first thing, otherwise do the second thing. All right, so this is the true case. That's the function that you'll apply in the true case. You'll give that back. True case, if only I can spell true. And here is the thing you take. This is your else case. Your false case. All right, so just take all those three things. Take the thing you want to do the if-else on, take what you want to do when it's true, what you want when it's false, and then here is your if statement. You apply the predicate to A and B, which is really cool. Isn't that neat? So the reason this works, I don't know if we need to get into it, the reason this works is because if it were true, right, you're taking your predicate, and if it were true, true gives back the first thing, right? You apply it to the first thing and the second thing. If it was true, it gives you back the first thing. That's what the function true does. And if it was false, it gives you back the second thing. And that's exactly what we want to do if it's false. See how that's working? That's if else. And so you can have that. I think, yeah, there's just a few more things that just keeps going. You can keep going. You can build all of computation. Let's do arithmetic. How do you make numbers in the Lambda calculus? They need to be functions, right? So we need to think about this. We'd like to have numbers. We want to represent 5 inside of our Lambda calculus. Like, what does it mean to be 5? Like, this is just a symbol, right? All of these are just symbols for 5. What does 5 really mean? All right? And so one way to define 5 that I think we've talked about in your book is, all right, 5 is just you start with 0 and you add 1 exactly 5 times. That is essentially one way to define what 5 means. So starting with 0, add 1 5 times. Okay? So we can represent the natural numbers which start at 0 like this. Okay? The natural numbers are functions, of course, because this is the Lambda calculus. They are functions of 2 parameters. Each parameter is not something that you're ever going to like take. Think of each parameter as an idea, like a data structure that you're building up. This is the easiest way to think about it. So every number, it has a body, but it first takes 2 things. It takes 2 parameters, S and Z we call them. S is the idea of adding 1. We call that the successor function. The +1 function. It's the add 1 function. And then Z is the idea of having 0. These are just variables that represent those ideas. And so you always start with these things, whatever they are. They're just things that you can think about. And then the body is what you really wanted. So if you give me something that represents the successor and 0, the number 0 is just Z itself. Yeah? Then you give me something that represents 0 and the successor. The number 1 is, well, start with 0, add 1. Apply that +1 function to 0. That's 1. That's what 1 means. Same with 2. Give me those 2 ideas, then start with 1, add 1 more. Successor of that. That's what 2 is. And then you can build up all the natural numbers like this starting from 0. Does that make sense? It goes on and on and on forever. It's just, all right, the number is successor, successor, successor of 0. That's 3. That's all you need. So that's how you can represent numbers in the Lambda calculus, and then you're off to the races because now we can add them. Here's the add function. Here's the plus function. It gives back the sum of 2 numbers that are encoded in this way. It's just all so nice. So let me show you what's going to happen here for plus. All right, let me add, let's add 2 plus 2. Why not? So example, 2 plus 2 in the Lambda calculus. What needs to happen? We say plus, and then we give 2, and then we apply that to 2. So these are the first 2 numbers that you take, and then it builds up a number, right? S and Z, that makes a number, and it does some stuff. Okay, so plus applied to 2 and 2 is going to be, well, what's 2 lambda s, lambda z, s of z. I guess we don't usually draw these inner parentheses in the lambda calculus, so we keep it like that. And then we'll apply all of that to 2 again. Lambda s, lambda z, s of z. Isn't that cool? So that's 2 plus 2. And we can keep on doing this. Keep on doing stuff. Because this has s's and z's, and we want to replace the body of things, plus also has s's and z's that are bound, though. Let's change some things around. This is, let's say that this one, for example, this number 2, it's equivalent to changing these variable names. It's equivalent to lambda x, lambda y instead of s and z. So instead of s, I'm using x, so x of y. And this will make it easier to think about. So I'll use that, and I'll substitute it now, okay? So one step. So bring this into the plus, for example. Or, yeah, let's go straight there. So this is going to be, this is lambda m, take some stuff, and so we're substituting in for this big body this value, okay? So that's going to become lambda n, lambda s, lambda z, and then what was m? This is the thing that's replacing m, right? Which is, we've decided to recall it this. Lambda x, lambda y, xy. And so do I have the proper parentheses now? So we have that, and then we give that to s. We apply all of that to s, and then this weird looking thing as well. So the m was only right here, which is nice. So s, then n, s, z, and that's the whole thing. And then we still have to apply it to this, which again we can rename. Okay, let's rename it to something nicer, because we have bound s's and z's in here that we don't want to touch. Those are not allowed to be touched. So let's call this, instead of s and z, let's use p and q. Lambda p, lambda q. That's going to be p of pq. Yeah? So that's our new thing. And then we'll go and replace this in for our n. That's the second number. So here we go. So that becomes lambda s, lambda z. And then this whole thing, there's the body, and we replace n with this every time we see it. Okay? So that's this again, lambda x, lambda y, xy, then s, and then now n becomes this. So it's lambda p, lambda q, p, q, and then we still have s and z. And I hope that I remembered the proper numbers of parentheses. Sorry if I messed one of those up. But that is almost the answer. You see how it's in number form? It's ready to take the idea of successor and the idea of 0. So we just need to finish off this body, compute inside of it, and then we have the answer, which should be 4, right? Are you ready? So I guess the first thing we need to do is, gosh, there are plenty of ways to go. So let's do this first. Let's take, starting from here, let's bring the s into this one. Let's apply that first. Okay? Let's bring the s in for x. Replace x in this whole body here. So that becomes still lambda s, lambda z. And then, so we have this body, which is lambda y, but we replace x with s. So s of y. See how we're getting somewhere? A little bit at a time. And then we have this, which, you know what, we can just also do this one too. Why not? Let's just do both at the same time. So we're putting this s in for p, for q, in this inner body, okay? This replaces p, this replaces q in the inner body, okay? I think you can imagine that that's what we need to do. So that becomes s for p, s of z. Ooh, there's another 2. What? what's about to happen here. So keep on going. These were actually a few steps that we took here. We just have one more thing to do now. We take this and we apply it into here for y. We replace y. Y becomes this. And look at what we end up with. Lambda s, lambda z. S of y, but what's y? This whole thing, we're replacing it, function application. S of, now all of y, S of z. That is equivalent to 4. That is the answer. That's plus. You can use functions to represent numbers and end up with plus. It's amazing. It's ridiculous, but it's possible. And you can do the same thing for multiplication and for power. It's the same kind of operation. It's like, all right, let S be add 1 really. Let S be times something. Things like that. There are ways to do it, and I'd be happy to talk to you about them during office hours. But I just want to give you a flavor of all of this. This is where computation can come from. It's very cool to think about. All right? Let's build up more data structures now. Pairs and lists. Let's make pairs, and let's make this happen. So here's how you can make a pair. A pair is, you give me the two things, this is the pair making function, you give me the two things that you want to make a pair of, and this function that I give back is the pair. It's a pair. All right? It represents the idea of x and then y together in a pair, where x is the first thing and y is the second thing. And then you can get the first thing out of the pair, like you need ways to extract stuff now. What's the first thing? What's the second thing? Well, you can get the first thing out of a pair by applying true to it. You can get the second thing out of a pair by applying false to it, which is really cool. It's all possible. All right? Let me maybe... Gosh, do I want to show you this one in Racket or that one? Let's try this one in Racket. So let's do pairs. Define pair to be lambda x, lambda y, and then lambda f, and then fxy. So we have f applied to x, then y. I believe that I have balanced everything. That's what it means to make a pair. And then the first thing, to get the first thing out of a pair, is lambda p, take the pair, and apply true to it. And then second is the same thing, but with false. So let's build up the pair like, I don't know, 2, 3. P2, 3. Let's define that to be pair of, well, take the 2 and then the 3. That's my pair, and I can extract stuff. Display the, this is supposed to be second, of first applied to P2, 3. That should give me the 2, right? Then second should give me the 3. What do you know? This is all possible just with functions. Just with functions, you can make whatever you want. You can build any data structure now that you can put multiple things together. You can make lists out of pairs. Like, what is the list 1, 2, 3? One way to define it is, all right, we can just make pairs, like the first thing and then the rest of the list. Here's the pair, 2, 3. That could be the list. That's how you could define lists. So now you have any data structure you want. You can extract things. I guess the last thing that I want to show you is that you can loop. Like, I think you can imagine that you can make whatever you want with and, or, and not, if you've seen all that before in like CSCI 45. But if you haven't seen that before, or you're just wondering how to do normal stuff, you can loop in the Lambda calculus very easily. Here is the easiest function to write that loops. It's like, all right, you apply this fancy function to itself. Well, this whole thing goes and replaces x, right, in the body. What does that mean? Well, all right, just take this body xx, and we replace this every time we see x. So we saw it twice, so we put it twice. Lambda x, xx, lambda x, xx. So this function evaluates to itself again and again and again until the end of time. So this function, it says, we say that it diverges, which just means it has an infinite loop. And so if you can loop like this, that means you can do normal stuff too. You can eventually have a loop that stops. as well. And that involves our good old friend recursion. In order to loop using functions, what do you know? We need to use recursion. That's what it means to loop using functions, doesn't it? So here, this is probably the hardest thing I want to explain. This is how you can recurse. This is how you can use recursion in the Lambda calculus. And this is very mind-blowing. I'd, of course, be happy to talk about this more after class. But let me get rid of these red things because they bother me. And here is what we want. We would like some function called fix that takes some function and does this to it. It gives back that function with fix of g applied to it. It's like you can bring the g in another time inside of itself. If we could do that, that would actually give us recursion, and that will take a while to think about. But it's like we can push the g, we could push the work inside of itself. That's kind of what's going on there. And so here is, let me prove to you, here's an example of g that we'd like to have this work for. Here is a function, okay? It takes two numbers, r and n, where r is a function and n is supposed to be a number, right? So here is the body of this two-parameter function. It's like if the number is 0, then give back the answer 1, else give back n times, apply the function, r, give it to itself, give it to itself, r of n minus 1. So that's the next smaller thing, all right? So this is like a recursive call here, essentially, but r is a variable right now. And so this kind of represents one step of factorial. You see how this is calculating n times something involving n minus 1? That's going to give us eventually factorial. So factorial of 0 is defined to be 1. This is one step of factorial. If we could fix this function, allow it to apply inside of itself, then we could have this recurse as long as we need it to. Okay? If we could apply fix to g and use that, that will give us the real factorial function. And let me prove that to you. Okay? This is definitely the hardest thing to wrap your mind around, but it's one of the coolest things in the Lambda calculus. So if we had a function like this called fix that did this for us, it would be mind-blowing. It would be awesome. So then I could apply f to 3, and that should give me back the factorial of 3. So f is supposed to be fix g, and fix is called that because it calculates what's called a fixed point of a function. It's a function that gives back itself. Have you ever tried to type a number into your calculator and you keep pressing cosine? Eventually it converges to a number. That number is the cosine of itself. That's called a fixed point. That's essentially what we're doing with just arbitrary computation here. Fix of g applied to 3, and this will eventually become this. Like if fix of g, we can define it like this. This is what it's supposed to do. It's supposed to give back g applied to fix of g of 3. And now we are off to the races. And actually, I think there is an error here. I think I wasn't supposed to have that second r. I think that is the way that it's supposed to work. And so if we keep on expanding this, like what is g but this whole thing, we give it fix g first, and then 3 next. So we have, we have the body. Replace n with this, replace this with r. What goes on? We have if n equals 0, and n was 3. If 3 is equal to 0, then we return 1. It was not, so we're definitely going to take the else case. Else we give back 3 times, then r of n minus 1. And r was fixed g. We apply that to n minus 1, which I think you can imagine is supposed to be 2, right? That will eventually become 2 anyway. And so we're definitely going to hit the else case, because 3 is not equal to 0. So with some more steps, we end up doing 3 times fix of g applied to 2, which is, what is fix of g? It's just g fix of g. G fix of g. And we're still applying that to 2, right? And what do you know? We have this all over again. It's another call to our original function g. That's what the fix is doing for us. It's allowing us to find that fixed point of a function. That's what it's called. All right. So let me just unfold this one last time, and I think you can see what's going to happen. it's going to be 3 times, and then g takes this as the r, this as the n again. So this is like if 2 is equal to 0, then give back 1, else give back 2 times fix of g applied to 2 minus 1, which is 1. And so eventually it's going to get down to the answer. And so again, it's going to give back 3 times. It's going to take the else case, so 2 times. And it's eventually going to calculate 1. Isn't that beautiful? So that's recursion. That's how you can make it happen. If only we had something for fix, something that actually did this. And here is one way. There are actually multiple ways to make a function called fix that does this. One of those ways is called the Y combinator. It's a very famous Lambda Calculus term. All right? It's one implementation of fix. So we call it Y because it's so special. And I don't think we have time to expand it. There's so much to do here. But the idea is you give Y any function that you want to create this fixed point of to make it recursive, and it will eventually evaluate to g of y of g, and it will give you back the right answer. That is the idea. That's what's going to happen. Let's see if I can try to go into Racket very quick and just like code this up and see if I can make it do factorial for us, just to prove to you one last time. But that is not something I'm going to have you watch. So I'll be right back. Let me try this, and then if it goes well, I'll show it to you. Okay, so I remembered the hard way that this version of Y does not work properly in Racket because it forces you into an infinite loop. Because normally with the Lambda Calculus, you get to pick like where you want to reduce. Racket and most programming languages pick for you where you want to reduce, and so it can lead you into an infinite loop even though you didn't want one. So there's another version of the Y combinator that looks mostly the same. Here it is. It's called the call by value Y combinator, and it's defined in a similar way. And here's my g. That gives me one step of factorial, and if I apply it, if I apply y to g to create that fixed point, apply that to 3, like this whole thing becomes factorial, apply that to 3, I do get my answer of 6. It's beautiful. It happens. Okay? So there's definitely not any time to prove to you why this works, but feel free to look it up, and I'd be happy to talk to you more about it in office hours. But now, hopefully, I have blown your minds a little bit. You know where Lambda comes from now, because it's creeping its way into a bunch of programming languages. Now you know its origin story, that it can model all of computation if you let it. Okay, with enough functions, you can do whatever you want. And so this is all that I want to do. This is the last new piece of information before next week, and next week is all about review. So I will see you in the review lectures.